So again, the importance of the power electronics, okay, is the first energy conversion. In energy conversion part, we converting the electrical energy from AC characteristics to the DC characteristics. We are gonna see what is the differences and why we are gonna talk about the changing from AC to DC or vice versa, okay, in a few slides, in the next slides. And we are gonna see how what kind of advantage these conversion would give us in order to transfer energy or actually use energy in different applications. Okay. The next part that is one of the most again advantages of the power electronic device in power system is the control and regulation that we have over the parameters. Okay, power electronics, because they are uh, all the devices and all the components are controllable. Okay, and you could have a very solid uh, control over all the parameters, all the important parameters of your electrical system. Because of that, the power electronic device are one of the most useful or one of the most favorable kind of like devices like in compared to the other conventional kind of like uh, uh, loads or like transition electrical transition lines. Now, and this control also give us a very good dynamic adaptability when we are dealing with change. Because when we talk about the power system, okay, we are talking about a dynamic system. Okay, there is always generation is changing, like the load is changing always, and you have to answer those changes. Otherwise, you would lose control of the main variables in your system. Okay, so these power electronic tools are very important because they could basically guarantee us to have a very good control and stabilize our system. Okay, now another advantage of the power electronics is that improving efficiency. Okay, we have a control over the performance of our device, so we could manage to have an optimized kind of like way of performance in our device rather than like in like a conventional, like for example, generator. Okay, you have to deal with the physical kind of like laws of nature. Okay, you can't control that. You have to like adopt yourself with those laws. In power electronic, it's vice versa. We adapt the performance of the system to what we want. Okay, because we have the full control over all the parameters. Okay, now, before I move forward, I wanted to like mention one point, and I actually wanted to ask you, anyone can tell me what are the most important parameters when we talk about an electrical system or electrical signal in general? No, parameters as physical parameters. Yeah. What are the most like important parameters that you have? Reactance is a secondary product of other parameters. How that reactance, what do the reactants do for you in the power system?
It changes the phase between the voltage and current.
Okay, so it acts on initial parameter. It's a secondary parameter that acts on initial parameter. What was the initial parameters?
Voltage,
Voltage, current. Okay, so voltage and current are two of the most important parameters or fundamental parameters in electrical system. What else?
phase.
Phase. Okay, that's true. Phase is the third one. Now, I wanted to like give you the better understanding of the phase. Okay, phase is not just an angle. Okay, when you talk about an electrical signal, like for example, a sinusoidal signal, normally you have the function is amplitude, a sinusoidal function, and its phase. But when we're dealing with the electrical system, that phase will divide into two parameters. One is the time variant parameters, which depends on frequency, okay? And the other section is the constant parameter, which is our phase angle. So this is phase. The whole part, the whole section is phase. Okay, phase is not just theta, the phase angle. That's phase angle or initial phase angle. Okay, the whole parenthesis is phase, so it contain both frequency and initial phase angle. Okay, and the frequency part would create a time-dependent section for the phase. So as time pass, the value would change. Is that clear? So the third one was frequency. So now we have voltage, current, and phase, or we could call it frequency because theta would not change. Okay. Now, what is the fourth one? The last one. When you talk about the electrical system or electrical power, what is the main focus of you when you wanted to develop a power system? What you want to do for loads? Power. So power is the fourth main parameters that we have. So all we do in our electrical system, when we talk about the stability, when we talk about the resiliency, when we talk about the analysis, okay, all those crazy stories, all those processes would pack into stability and analysis of voltage, current, frequency, and power. Okay, that's our goal. We have to keep these four under control on our desired domain. Okay. Now, what are the application of the power electronic? Now, I kind of like get a little bit of off the road to give you the idea of what we're talking about, but let's back to the power electronics and the application. What are the application of the power electronics? One application is renewable energy. Okay, we use power electronics for integration of the renewable energy into our conventional power grid system. Okay, now the most important type or the most popular types that use inverters or power electronics to get integrated to the system are solar system, because the output of the solar arrays are DC voltage, but our power system is AC, so we need to convert that DC to AC. Okay. Another one is wind energy system. Now, I want to ask you one question. The wind energy turbines, they are induction machine or like double effect, induction machine. They are like conventional generator. So they create AC signal at the output. And our system is also AC signal. So why we need inverters for power electronics if we wanted to like connect an AC generator to an AC system? Match phase, that's a general correct answer. Any more detailed answer? Any one of you knows why we need? You go. Exactly. Because we can control the speed of the wind. The speed of the wind would determine the speed of the generator. And the speed of the generator is the same speed as the frequency of the generated electricity. So we have a fluctuating, non-controllable frequency at the output of our generator. What we said a minute ago, we need to keep frequency was one of the 4 important parameters. We need to keep frequency stable at our desired stage, correct? So wind generator alone are not good at all because we can't control frequency on them. What we do, we change whatever AC signal that the wind generator creates, we change it to the DC to eliminate the frequency, and again, change the DC to our desired AC. Now we have a control over that frequency. Okay, so that's why. Also, energy storages. Energy storage is also, again, one of the most kind of like popular application of the inverters and power electronics, okay, in the renewable energy system. Okay. What else? In a smart grid application, okay, other application of the power electronics or inverters in our power system is to have a grid stability, to control the grid stability when we dealing with this in a smart grid kind of like control situation, okay, to control the power quality, okay. We said power is one of the most important, right? Okay, so we need to keep that at our desired level. Okay, we'll talk about that, why it's important later, but the quality of the power is going to be controllable, or we could compensate any fluctuation or any variation from our desired point, okay, or setting for power using the power electronic device. Okay, those power electronic devices that work on power quality, they normally known as FACTS device, flexible AC transmission system. Okay, you could search on that. These are very actually good area of work if you are interested in power electronics. Next application in smart grid is distribution. If we have smaller grid, okay, now we need smaller generator, solar mostly and wind, and we need micro inverters, as we talked about that in previous slide, to connect those microgrid into our loads and transmission lines. Okay, and we'll have to control over all the 4 parameters that we have when we're dealing with a microgrid. Because microgrid, let me give you one example why we need micro inverters and power electronics if we're dealing with a microgrid. Okay, let's consider the voltage. If you have a very huge generator, okay, let's consider like a power plant. In a power plant, you have a very huge turbine and generator, okay, that creates a certain voltage at the output. Now, if I create a temporary fault at the output of that generator, or I create any kind of fluctuation at the output of that, on the load of that generator, okay, what's going to happen to the voltage? The voltage, like if I increase the load suddenly into our generator, anyone knows what's going to happen? You don't need electrical actually knowledge to know that. Like we have a generator, we have a source. Suddenly we increase the load. Voltage drop. Voltage drop. Why? Because the generator temporarily would be overloaded until the control system would adapt to the new condition. The voltage would drop. But because you have a big, huge power system or like huge dose generator, okay, consider this. The inertia of that generator would handle a part of that fluctuation. So the voltage would not drop to 0 or like very low. Because you have an inertia, an energy stored in your generator that could handle that fluctuation to a certain level. Okay? Now, if you have a microgrid that doesn't have that much of an inertia, a bulk power grid has huge inertia. It can handle small fluctuation. Okay? But if you don't have that inertia, what's going to happen?
Drop to zero.
It dropped to zero. How we could deal with that? We have to fastly adopt the new, situation. Or actually predict in some cases that like in current studies, they try to predict the fluctuation or answer it in a sub-cycle, kind of like before one cycle of the sinusoidal. Okay, so the system would not even see that fluctuation. Okay, what can help us to that on that? The power electronics, because they are fast, controllable, devices. Our system is 60 hertz. Our switching power could go to the kilohertz when we talk about the switching devices. Okay, so we could have a relatively very fast response to our fluctuation. Now, any questions so far? No? Today we are mostly is introductory, so we don't have like much of a detail, but these are like kind of like the main categories that you have to like keep in mind. Okay. One of the other application of the power electronics or inverters or other kind of like converters in the power electronics is the EV system, the electrical vehicle. Electrical vehicle completely relies on power electronics. Okay, because they have to store energy and they have to do it in DC form. Okay, and because they have to control the speed, they have to convert it to an AC system for the actuator. Does that make sense? So they always try to change DC to AC, or like recently, because they wanted to like add efficiency, they had a system in their brake, like Tesla had a system in their brake. When you hit the brake on a Tesla, that energy that's supposed to be lost between the length and the wheels, okay, the brake and the wheels, they reverse it to charge their battery. So they have like a AC to DC converter too. You know what I'm saying? So bi-directional system to increase their efficiency. But what I'm saying is that the EV is also one of the important application of the power electronics and inverter specifically. There are more kind of like routine applications of the power electronic too, like these adapters that you use for your laptop or your cell phone, okay, to charge your cell phone. They are all power electronics. They all are switching device, either changing the AC signal on a plug into a DC voltage that your device could handle, or they kind of like try to like regulate the voltage or like, control, stabilize those four important parameters in your system. So these are like, there are an industrial application, like drives for the machines. There are consumer, like what we said, the adapter that we charge our devices with, and there are tons of other applications in routine application that you have, like any kind of a smart kind of like system that you have, it has to have a power electronic for the for the power supply sector. Okay, so it's a very wide field regarding in perspective of the application when we talk about the inverters and power electronics. Okay, any question?
Question. On the chargers, I had not heard of that. Is that just the chargers that are like out in stations, or is that those chargers that are at people's houses, or
Everything.
all of them?
All of them, because the batteries in their in the EV, they have to store DC energy. Okay, they work in DC. So if you want to charge it with your plug-in, you have to convert it from AC to DC. So
No,
then,
I meant the part about stabilizing the grids during peak demand. I didn't know they helped with like stability. like stored, acted as a storage unit, stabilized.
Which section that you
It says vehicle, no, next one. The vehicle to grid integration.
oh, bidirectional charge lock. Okay, this is like this is also a new trend. Okay, I forgot to mention that. Thank you. For they try to use the EVs instead of just a load as a load slash source, auxiliary source in the grid. Like for example, you charge your EV machine, okay, you are connected to your EV machine, your charger at night at home, okay. Typically, we say, okay, the vehicle is a load. It gets charged from the grid, okay, but they try to use a bidirectional setting. So if for any circumstances, okay, your immediate network, power network, like a household, okay, sees a fluctuation or needs an extra auxiliary fast kind of like energy source, it could use your car as a battery, okay, to drain that, to kind of compensate that inertia that we talked about, okay? So your car would kind of like develop a temporary inertia to deal with the fluctuation and then go back to the load section when everything is fine. Did I answer the question? Yes. So this is not quite popular right now. It's not like a wide like distributed kind of like technology. Is new. You know they are talking about it to see. This is still in a research kind of like phase. Okay. Now, as useful as power electronics are and inverters are, they also have challenges when we want to like use them in the system. One is the reliability because they are switching devices, they have their own sensitivity. There are factors that could affect their performance. One of the most important one is the temperature. Okay, so you have to deal with the temperature. You all know that like you have your laptop adapters and it gets hot. You have your cell phone adapter, it gets hot. Switching device has a huge amount of kind of like temperature generating in their switches. Okay, so we have to deal with that. Otherwise, we get in trouble because not only it could create a fault, but also it would affect the performance of the device. Another one is the switching devices are semiconductor devices. Okay, so they are silicon-based or germanium-based devices. Their application is based on an unstable or semi-stable voltage. A huge stress over the semiconductor could break. You already know about, I think you all work with diodes. Did you work with that? Anyone that didn't work with diodes? We are gonna see that, but like the diodes not only have the breakdown voltage, okay, but sometimes they have like a residual leakage. Sometimes they have the avalanche breakdown. Have you ever heard about those topics? Yeah, okay, so they are very sensitive to the voltage stress. If it increase if you have like a very high voltage stress, it would create a breakdown in a semiconductor. Okay, and when I say voltage stress, I don't just mean the amplitude of the voltage. Okay, it is amplitude of the voltage. In high amplitude, it would break down. Also, in a very sharp high changes. So the gradient of the voltage would have a high value. That would also create a problem. You could see in the YouTube and like search about the high gradient of the voltage. Okay, and you can see. Or one way to like experimentally see it is if you have like a you saw the bars or the bus that the high power devices, probably you saw that. used, they are normally are round or has a smooth edges. Okay, that's because of the gradient of the voltage. If you have a very sharp edge with a high voltage, okay, you actually can hear that the insulation is not breaking. You hear that corona effect over your conductor because the insulation are breaking. Why? It's not because the voltage is too high, it's because the voltage is too high in a very small area, so it's the gradient of the voltage is too high. Is that clear what I'm talking about? So now, another part is the cost. When we talk about the power system, buying a regular, like an electronic size, or like in a communication circuit size switches, like MOSFET or BJT, or like, IGBT in the low power system, that's not expensive. But we are talking about the power system as we talk about like the kilowatt energy transfer or megawatt energy transfer. Okay, we talk about the different scale of the switches. Okay, so like the inverters in a megawatt scales could be as big as this room. Okay, so this is what I'm saying. Like now we are gonna have a problem talking about the cost of those switches because it's hard to make them, Plus, the one of the most important, actually, because people are already deal with the reliability of the thermal and like voltage stress in the technology that they develop. Okay, so these are already somehow answered. Okay, the cost is reasonable now. There is room to have more efficient cost, but it's reasonable. The most important problem that now power system face when we talk about the power electronics and inverters is the third one, the grid integration. We are going to see why, but to put it in a very brief description, the switching device, as I think we mentioned that before, creates harmonics, creates distortion because they cannot create pure sinusoidal voltages. Okay? Now, what that means if you have a power electronic device that is supposed to create a power signal or energy signal in 60 hertz, not only will it create that 60 hertz signal, it would create 120 hertz or 180 hertz or like all the integer multiplication of that 60. Okay? And let's move a little bit deeper. When you talk about the harmonics, the general way of dealing with the harmonics is the multiple integer. I assume you know about this Fourier series. If not, we are going to cover that. That's not important. But Fourier series is the distribution to equivalent an arbitrary voltage or a signal with a summation of a bunch of sinusoidals with different frequencies. You have fundamental frequency and all the integer multiple of that frequency. When you add all of them from fundamental to the infinite frequency, then you could recreate that arbitrary signal. Okay, by adding all those sinusoidals together. Okay, now when we talk about the power grid, it's not just those frequencies. They are harmonics. They call harmonics. We have inner harmonics. They could create inner harmonics. We are going to talk about that. What are inner harmonics? I'm just going to give you the keywords. Inner harmonics are non-integer multiplication of the frequency, the fundamental frequency. So it's not like the converter could create 60 and 120 and 180. No, there is 100 hertz too. There is a 99 hertz too. Okay, the amplitude are different, but it creates a lot of other frequencies and injected into the system. Now what's going to happen? If you have several inverters, they all inject those signals with different frequency, okay? And all those frequencies are interacting with each other in your system, which creates some problems that we are going to deal with in after midterm kind of like situation, like the concept that we talked about. Plus that system inertia. The conventional generators, because they are physical, they have physical weight. Either they're a generator like a turbine or like, they have physical weight. They have a physical like inertia. Switching device is just cut on and off of a signal. There is no inertia. So if we switch all the power system today from conventional one to the renewable like solar and wind, okay, wind have some sort of like inertia, but like let's say solar that doesn't have any sort of inertia, what's going to happen to our four parameters? Then we would have a lot of problem when there is any fluctuation, because now the system doesn't have any weight, any inertia to handle those fluctuations. Any flicker or like any fluctuation here would, immediately goes to the source, and it like, because it doesn't have a weight, consider that like if you have like a huge ball here, it's hard to kick it and make it move. But if you have like a very thin, like a very lightweighted ball, any small kick would throw that ball far away. Same goes with this stuff. Any fluctuation would shoot your power electronic system or like generator system far away from your desired point of performance. So these are the problems that we are going to face, and we are going to see how to answer. Okay, in this course. Any question? Yeah. Okay. Now we said that one of the fundamental component, fundamental concept that made suggested to us that we use power electronics in our power system is when we want to like change energy from DC to AC or vice versa. Okay, but why we have to do that? Okay, this is the fight between Tesla and Edison, if you know about it. Edison says DC is the DC rules. Tesla says AC rules. Okay, who's right, who's wrong, and what we have to do. Okay, what is the best option? Let's talk about it. What is AC and what is DC? I assume you already have the knowledge, but I'm gonna briefly mention that. When we talk about the DC system or DC directed current, we talk about the current that do not change direction. Flow of the current do not change direction. When you had like a DC supply in your system, or like when you wanted to draw a DC, you always draw a constant value. Okay, this is how you draw a DC voltage, and you know the DC voltage, like for your DC current, has a constant value. Is that correct? That's not true. DC could have fluctuation. The point is that it shouldn't change the direction, the flow of the current shouldn't change. So that's this signal with all the fluctuation is also this, because it doesn't change. The flow doesn't change. It doesn't go to the negative part. It's always moving in a certain specific direction. Okay. That being said, in practice, you never had that pure perfect DC. You always have fluctuation. We call it ripples. Okay. Now, how about AC? When we have AC, the flow of the current alternates. Okay, the direction of the flow of the current would alternate. So sometimes it goes from the source to load, and a part of time it goes from the load to source. This is the basically the very simple way to define AC and DC. Now, since we have the change of a direction, that means we could describe a cycle for our AC correct? And if we have a cycle, that means we could have a frequency. We don't have frequency in DC, but we have it in AC. Or if we wanted to like be very true, frequency in DC is equal to 0. Okay? This is kind of like the same. So the differences. The flow of the direction are different from AC/DC. The voltage behavior different. In DC, we don't have positive negative change. In AC, we change from positive to negative, and vice versa. We have frequency in AC because of that alternation. We don't have frequency in AC in DC, or the frequency is equal to 0. Now, when we say we have frequency in AC, what other differences could come to your mind because of that frequency things between AC and DC? In DC, we don't have frequency. In AC, we have. Now, since we have frequency here, what changes we could see in like our circuits? What was the component in the circuit? We had three main components in our AC circuit analysis, correct? Capacitor, inductor, and resistor. Okay? Resistance doesn't rely on frequency. It does, but we say it doesn't. Okay? So, because it's negligible, kind of like, we could just see that. If you wanted to see how it does, search skin effect. Okay? So, resistance, we say, okay, it doesn't have any change in it, doesn't rely on a frequency. When you have a DC system, how capacitor would behave on a DC system?
It's
Open circuit. How the reactance would work in a DC? Short circuit. Now, why is that? Because if you want to use the frequency domain value for capacitor or for inductor, okay? For capacitor, you have 1 over j omega c. What happened? Okay. And for conductor, you have j omega L, correct? In DC, omega is 0. So here you have infinite impedance in capacitor. In reactance, you have 0 impedance. Open circuit, short circuit. Now when we have AC system, now we have a value other than 0 for our frequency. Okay? So now our system is depending on a frequency. The model that we have for our system depends on frequency. Put that next to the concept that I said that power electronic system would introduce not only the fundamental frequency, which are desired, the 60 hertz, okay, but also create harmonics. So you have one inductor, but that one inductor would have one impedance in 60 hertz, another impedance in 120 hertz, another impedance in 100 hertz, that inner harmonics. And how you can manage all those impedances? We said in AC circuit analysis, we don't mess with frequency. So we analyze in each of those frequency, we analyze our system in each of those frequency, and then use superposition and add all of them together to see what's going to happen overall. So see how complicated things could get, because now we don't have one aspect. Okay, so it's going to be a huge mess when we have this. So this is one of the complications. Now, for energy transmission, okay, because the dominant impedance in a DC system is resistance. Okay, and in the AC system is normally inductance. Okay. When we talk about the resistance, we talk about the wire. In short distances, the resistance is low, so the impedance of a transmission is low, so DC works perfectly. It's better than AC. But in long distances, not much. Okay? We could manage that. HVDC, okay, is a technology that somehow help with that large distance DC transmission. Okay, but generally DC is used for short distance energy transfer. AC is for long distance energy transfer. Okay, but if we want to talk about the AC system, we said in a DC system, the capacitor and the reactance wouldn't affect our system because the omega was zero. But in AC, they are working. They do affect the system. How they do affect the system? Anyone can remind us how the go ahead. The phase displacement between the voltage and current. What was the product of that phase displacement? What was the effect of the phase displacement between voltage and current on our four most important parameters on the power? Okay, we are going to talk about it. Changes to angle. We are going to talk about that. Don't worry about that. Okay, but what it changed is that in DC, you only have active power because you don't have any phase displacement between current and voltage. They are synchronous to each other. When you have in AC system, when you have L or C, now the current and voltage are not fully synced with each other. They have a phase displacement between them based on the value of L and C in the system. Okay?
Don't industrial applications like reactants, like if they have too high reactants, it pushes power back into the grid instead of pulling it.
Back, there's no power back. I'm gonna tell you one concept that actually do reactance and that phase displacement between the voltage and current, okay, creates a deviation in the power, which we call it reactive power. So now, before all the power that we generate in DC, all of them would be active power and flow through the system. Now, because of that phase displacement, we have to spend a little bit of, or like a large amount based on the phase displacement of that energy that we generated to deal with that phase displacement, so we could actually transfer our power to the load, from source to the load. So we have that total power, which we call it apparent power, and we show it by S. Now includes that active power that works for us, that we know about it, and the reactive power that we need to deal with that L and C and that phase displacement, okay, in our system.
That's why industries that extra charge in our system.
There is no extra charge if they want to look the compensation of the reactive power.
No charges in like cost wise from.
Yes. There is a standard. If you have like a harsh load, huge load, or like an industrial load, okay, the regulator mandated that you have to keep your power, reactive power, under certain limit. If you go over that threshold, they would add more cost, kind of like a penalty to your bill. Okay, it's not going to happen in a household because household doesn't have that much of an L or C, okay, effect, or like a reactive power consumption effect. Okay, but industrial does. Okay, now how to compensate that? Remember, if we if that L and C would deviate our energy from active power to reactive power, that means our power quality is getting lower. Does that make sense? Now, what did I mention that it could be useful to compensate that, to fix that problem? Facts device. They could compensate that difference. So we have a higher, again, better power quality in our system. Okay, I'll give you the general ideas. Okay, this course, this session is general idea. We are going to go deep into those concepts. Okay, any question? No? Okay, we already kind of talked about that. In AC, we have alternating voltage and current. This is one of the characteristics. We have frequency in AC, so our system is frequency dependent. Because of the frequency dependency of inductance and capacitance, we would introduce reactive power into our system. Reactive power, I want to tell you that I use this example in an energy conversion. I'm going to use it again in order for you to know what the reactive power is. Okay, apparent power is S. Let me, because we have another person in the Zoom, so let me use this one. Apparent power is S, and we say S is the total energy. Okay, the apparent power. When we have AC, we have reactive power, so the S becomes P plus JQ. Okay, this is reactive power, this is active power. Okay, is a complex power. We also call it complex power, S complex power 2. Okay, and J is the square root of -1, the complex number. Okay, so J is the square root of -1. Now, the example that I use to show what is actually the reactive power is a cup of beer. Okay, I'm sure you don't have beer, you will not have it, but if you see it in the videos, okay, or in the YouTube, you will see that the beer has the usable kind of like stuff like the beer itself, plus a little bit of foam. Okay, this is the capacity of the cup is S. The foam is like Q, the reactive power. The beer itself is like P, active power. The people that like beers, they want beers, not the foam. Okay? But no, okay. But you can't have beer without having the foam because it's needed. If you wanted to create a beer, the natural process would create a foam. So you have to have a foam in order to be able to have a beer. So you can't get rid of that. It would take capacity of your mug. You can't drink it. P is the active power that you use in your system. Is what does actual work for you. But in AC system, if you don't have the reactive power, your environments are not capable of transferring that active power from source to load. So you can get rid of the reactive power. You need it to create the environment suitable for transferring the active power. It's not useful in like a direct kind of like perspective, and it takes the capacity of the system. So when your active power is high, you have a lower capacity in your system to transfer active power. And that's why we call it like a power quality issue. Okay, so now we compensate, we reduce the reactive power as much as we can by compensators. So we get a better situation. Are we good? Any question?
So this makes better, so the foam is Q, then the actual liquid is.
P. Yeah, it's the same kind of concept. Like the people, not us, the people that wanted beer, they wanted the liquid, not the foam. The people that want power, they want active power because that's what it works. They don't want reactive power. But we can't have active power without reactive power in a system. We need it naturally. Okay? Can I answer your question? Are we good? Any question? No? Okay. Oh, the fourth thing about the AC system versus DC system is that if you want to like transfer AC energy, is much easier to transform or modify the level of the voltage in AC rather than DC. Okay, it's a simple transformer could modify the level of the current and voltage, but in DC you have to go to the hell of a kind of like conversion, you know. Now, the characteristic of DC is unidirectional flow, is basic of the DC. In DC, we have a better voltage stability because the fluctuation is limited in a certain margin because we should not have changes of direction. So the maximum fluctuation that you have is to go to zero. Okay, so it has a better stability, basically. We don't have reactive component in our system when we talk about the DC. And the limitation is the distance. In long distance, you would face a huge power loss, so it's not good for long distance. I'm gonna move away from this one. You could see that I already upload this PowerPoint into the Canvas, so you have access to that. Okay, so you could read that. Now, we already also covered this so far, like what are the advantage of the AC over DC. We already talked about that. So again, read that by yourself. Let's go to the power electronics components. Now, so far, we said what are the applications of the power electronics? The main one was the AC to AC conversion. Okay. We said why AC DC? We talked about the AC and DC and what are the advantages and disadvantages of each other. Okay, with each other. Now we are gonna say, okay, now we know what we have or like what the use of the power electronics are. But now let's talk about, okay, what is the component in power electronics? The main difference between the component that we so far work in the AC circuit analysis, okay, and power electronics is the switching devices or semiconductor devices. Okay, so in a conventional power circuit, you have resistance, inductor, capacitor. Okay, you might work with a diode because it's the simplest semiconductor device existed. Okay, so but diodes also considered as a power electronic device. So what are the components in power? The first one, as we said, is diodes. What diodes? Diodes are a unidirectional component. So it let the current flow in a certain direction, and in a reverse direction, it would block the current. Is that clear? So we have a diode that a unidirectional component. What is the basic use of that? When we say unidirectional, and we talk about the power electronic and AC-DC conversion, how we could use the easiest use of the diode. That's the actually.
Switch it on.
Diode doesn't switch.
AC to DC.
AC to DC rectifying is the easiest easiest rectifier is a simple diode because it doesn't allow reverse current. So if you have a diode, apply AC voltage, it only allows like the one of the direction, either the positive cycle or a negative half cycle to pass. Yeah. But what is the limitation of the diode? You don't have control over diode. It works naturally. So if you have forward voltage, it will let pass. If you have reverse voltage, it won't let pass. No other control. Okay, so the level of control is low. Another type of device, there are tons of these semiconductor devices. I put a reference book. Actually, I put a lot of reference book in the campus, but one of them is the power electronics that I actually mentioned in the module of the first week that this is the reference. Chapter 1 of that book talk about all the different type of semiconductor component. Okay, and you could go over that review that there are tons of components like triode, tristor, BJTs, GTOs. There are tons of other components. What we are going to work with in this course are the component that I show here in the PowerPoint. Okay, so the first one is diode. The next one is MOSFET. MOSFET, I assume you already read, or it's easy to actually know how it works. We are going to cover that a little bit. MOSFETs are the semiconductor that you could control on and off when you talk about the letting the current go or not. Okay, on diode you don't have a control of on and off. Is the voltage that dictates the on and off. On MOSFET you have the control. So if you give a proper signal to the gate of the MOSFET, it would let the current pass, so it goes to the on switch, on state, and let the current pass from collector to the drain. And if you reverse the signal or like cut off the signal, it would block the current. So you have a control with the gate signal. You have control of when to turn on and when to turn off the circuit. Is that clear? The third component, which is the most important one, is IGBT. It's type of transistor. Typically, like generally, you could say it's similar to MOSFET, but it's different technology. Okay, it's different technology. IGBTs work like a MOSFET, but in better in a more efficient way. Okay, so when you talk about the MOSFETs, I don't know if you get deep into the MOSFETs or not, but when you want to model the MOSFET, the semiconductor device with the equivalent circuit, you have a certain amount of impedance in the input of the MOSFET that model the switch, and a certain amount of impedance on the output. And by the characteristics of the semiconductor, you could go to the you can't switch faster than a certain level. Okay, because of the nature of the semiconductor. If you want, we could talk about that later. Or, I'm gonna upload some videos in the details of why it would change. Okay, but today is introductory. Okay, the IGBT technology would make those components more efficient. So in IGBT, it would combine the high impedance input of MOSFET, okay, and low losses of BJT. So losses in a MOSFET are higher. What that means when we say higher losses in MOSFET regarding IGBT or BJT? Sorry? Less efficient, but what is the immediate impact of having a loss, having a power loss? Heat. You remember it was one of our challenges, or the sensitivities of the power electronic component. So MOSFET has a bigger problem with heat than IGBT or BJT. Okay, in fact, it's hard, like regularly you don't see any BJT with a cooling system. But MOSFET always needs a cooling system. You see what I'm saying? So this is kind of like the operation. When IGBT is also similar to MOSFET, so you have a gate. Based on the signal that you send to the gate, you could control the on and off states of IGBT, similar to MOSFET. Okay. Now, let's move, like, look a little bit deeper to the diode. This is how we show diode, the symbol. Okay, and we said diode is a unidirectional device. So how it works? If the voltage is in forward, okay, it would let the current pass, but it needs a certain amount of voltage, okay, to get on. In silicon-based diodes, that voltage is 0.7. In germanium-based diodes, the voltage is 0.3. Okay, so we are gonna go through the hardware. What that means when you wanna like choose between the two, if you need to have a diode that is getting on faster and is more sensitive to the forward voltage, germanium is the choice. Is the choice that you have to make. You see what I'm saying? So this is the type of mindset that you have to like have. Now, in your reverse part, if you change the direction of the voltage, it would cut off the current, okay, until the voltages get big enough to break the whole system, to break and cause like an avalanche breakdown in the semiconductor. So it cannot resist against that amount of voltage. For example, like if you have like a minus 50 volt over that diode, that simple silicon diode, okay, there are differences. The models have different breakdown voltage. Okay, this is one example of one model. It would break down to the in the avalanche kind of like situation, and then the diode is done. It's burned out. Okay, now based on that, we don't want to go near this part. So our preferred area that we want to work is this area. We wanted to avoid, when you design, we wanted to avoid going near the breakdown voltage when you talk about the diode. MOSFET has more complicated technology, or like kind of like configuration. We have two types of MOSFET, N type or P type. You could search on that what that means. I put the structure and the symbols. You could see different type of symbols. Okay, the P type, N type shows the direction of the current that goes from either like the to the drain or from the drain. That flash shows the direction. Okay, so it shows the direction. We have two types of MOSFET: enhanced type and regular type. Okay, there are two type of symbols showing those. So when you see those symbols, it would show what kind of MOSFET you have, and the direction of these flashes would show if it's P type or N type. Now, how they work? If you apply a certain voltage, a certain amount of voltage to the gate, it would let the current of the drain go to a certain level. Is that clear? So, two things that is important in these characteristics. One is that you can, after this threshold, you can turn on. Before that, you can turn off the MOSFET. So by this threshold voltage, okay, when you apply this threshold voltage and offer that this threshold voltage to the gate, you basically turn on the MOSFET. This is one control to have in MOSFET. The second control is that you could see that the characteristics of the current to the voltage gate is actually semi-linear. So it could also work as an amplifier. So when you have a certain signal in a gate, it gives you a different amplitude of the signal as a current. And the ratio is the gain of the MOSFET. So two things that gives you the two type of control that MOSFET gives you. One is on and off. The second one is the gain that you could see from the MOSFET based on the signal that you injected to the gate. You could have desired current in your output. Okay? But generally, after a certain amount of current, okay, the MOSFET gets saturated because it has the limitation. You can't conduct infinite amount of current into a certain device. It has a mass, has a capacity. Okay, so what's happened when it fits, when it fills, when it reaches the capacity? Okay, then you cannot go higher than that for the current. So the current gets saturated, but if you add more voltage to the gate, it causes the voltage over the MOSFET to get increased. It wouldn't allow more current, but it just allow more voltage. We don't want to get to the saturated region because it is the kind of like the harmful station of the for our switch. Is that clear? Are we good? Any question?
So we don't want to get it to the saturated region.
No. We keep it close to this line. We keep it close to this line. Now, IGBT is kind of similar to the MOSFET, but as we said, with different technology. Same as MOSFET, we have a threshold for a voltage of the gate in order to turn on and off. Okay, so you could see that the characteristics of the current that is drained from the IGBT versus the signal that you get to the voltage is somehow similar to the MOSFET. Same kind of like how to say, same kind of behavior. Okay. When we talk about the when we talk about the output characteristics of the switch, which is the current that is allowed to flow versus the voltage over the switch between the emitter and collector. Okay. This is the on part. When we get on and the current starts, after a certain amount, like the MOSFET, the current gets saturated, so it won't allow any current. Why we don't want to get far in this saturated mode? Because after a certain voltage, the semiconductor cannot tolerate that stress and it would break down. Okay, so we wanted to like keep it near this area. We don't want to go there. Are we good? Now, as we said, there are some complications when we talk about the switches. The thermal situation, thermal management is one of the biggest one and the immediate one. We have the switching. We would face a lot of power loss in switching, increase of a temperature. We have to deal with that unless our system would break down or like have a less efficient performance. The switching loss itself, regardless of the power, the temperature that they raise, the power losses itself is not suitable for us, is not desirable for us. For we have to like kind of like deal with that. Because MOSFET and IGBT needs a input signal to the gate for control, that means we have to have another circuit that could generate that signal based on our desired kind of like performance. So when we talk about the MOSFET and BJT, not only we have to have those components, but also we have to have a control circuit to create the signal for the gate in order to get what we want. And we have to get protecting mechanism. How protecting mechanism? One was to avoid those breakdown or saturated kind of current system, or saturated current system. Another part is when you want to like turn on and off the current flow is not like you say off and it's off. There is an energy kind of like that conducting through the system. So when you send a signal to off a switch, turn off the switch, you have to have a system in order to handle the decrease, the gradual decrease of the current, okay, over the time until it fully gets to zero. That gradual decrease, okay, ideally is not desired. So we have to deal with it. We call it a snobber circuit. We are going to talk about that. We have to deal with that gradual kind of like decrease that we don't want it to protect our performance on a circuit. Are we good? What? Okay, you have you could read these by yourself. Is not that important to our discussion. I already put that. We already talked about the most important introductory concept that we want. And that's it. That's it for today. Next session, we are going to talk about the inverters itself. We are going to go over a little bit details to the topology and the components, and then move on to the how we could control those components. We said we have a switch. We need a control circuit to turn on and off those switches. We'll talk about that, how to control it. We'll talk about the topology of the switches that we need to create an inverters, okay? And we talk about some of the challenges that it makes for us in the application of those inverters, applying those inverters to system. Thank you very much. Have a good rest of the day. If you have any question, just let me know.